All right, so we are going to talk about network foundations. I'm going to run through an actual workshop just to give you a sense of how networking works, some of the basics, as well as how this all functions in the world of Kubernetes, because you're here for Civo Navigate. What's up? Oh, you need the QR code, okay. You're here for Civo Navigate, and Civo provides basically Kubernetes and compute. And they simplify the networking so that you can provide the intelligence on top of that. Anyways, so one thing I will point out is that I actually was supposed to have a co-speaker. Unfortunately, they were not able to get their visa to come join us. Her name is Bhavya. Follow her on Twitter if you're on Twitter. She does a lot of advocacy around open source technologies. She's also a solo ambassador and a We Make Devs ambassador that's run by Kunal. My name is Marino Wijay. I am a platform/developer advocate at Solo. I'm also an ambassador at several other programs. I run a conference, and it's going to be an annual conference now called KubeHuddle. I also run some meetups up in Canada, up in Toronto, where we get a bunch of folks in the Kubernetes space together, blah, blah, blah. And by the way, I'm a network specialist. I've always been a network specialist, but Kubernetes kind of pulled me towards its little domain. And how I learned Kubernetes was by following the packet, that first initial packet. How is it moving around? And so that's why I felt it was necessary to build a workshop that was focused around Kubernetes to give you a better insight as to how things work. So you already got the link. Let's review the OSI model very quickly. So this is the traditional model of the OSI, the traditional networking model, the OSI model. There's another one called the TCP/IP. I still use the OSI model, the Open Systems Interconnect model, because it's very, very it reflects the ecosystem of network technologies very well. It represents those technologies extremely well. And if you actually look to the far right, you can see how some of these layers are aligned to what's in cloud native. But I'll start with the very, very bottom, the physical layer. When I bring up the physical layer in this OSI model, I'm referring to all these ones and zeros that are transmitted as electrical signals across the wire between devices. There's not much intelligence there, just a bunch of ones and zeros, but when you map that binary together, it's instructions, it's payload data, it's decision making, it's policy, but just in binary. But we have a way to transpose that into the network layer through the data link layer, which actually ties these electrical signals to hardware, to actual hardware. So for example, your MacBook over there, mine here, maybe your iPhones or your Android phones, they all have something called a MAC address, which uniquely identifies it locally. It's a locally significant address, which no one else knows about except if you're connected to something called a layer 2 network. So that MAC address is a burned-in address that helps you identify local entities on your network so you can communicate across to them. Except we don't ever use these MAC addresses to ever communicate directly, because who's going to remember a whole bunch of hexadecimal? So this is where the network layer comes in. The network layer is where we append an actual logical address to this MAC address. So the reason why we do this is so that we can determine how to get to that address. How to get to that address means I have this laptop in front of me, I'm connecting to a web browser, and that web browser is going to take me to a website. That website is not local to me. It's not localhost, it's somewhere else. And so I need to find a way to connect to it. So the network layer allows for that to happen. It's like everyone now has phone numbers. I have a phone number, you have a phone number, you might have like 3 if you have eSIMs or something like that. But the reality is we will never ever remember our friends' phone numbers. We remember our friends' names, address books, right? This is why DNS exists. So we have this network layer that gives us the ability to find entities across local networks and across remote networks. We have this transport layer which helps us identify protocols that we're using to communicate to other entities. They are signifying, or they're indicating the type of application I might be trying to communicate with using a particular protocol. You are very familiar with TCP port 80, which is the HTTP protocol. You all are familiar with SSH, right? You're all familiar with port 53, UDP port 53, what is that? DNS, right? So these are ports. These are how entities communicate across to other entities. Because we're never going to directly use their IP addresses. It's a way to get to them. But if we're trying to access a service or an application at that entity, at that endpoint, that's where the port number comes in. This becomes relevant later on. We don't really care much about the session and presentation layer because as operators, we don't have significant influence over those aspects. Developers do, because the way they package the application, the way they build out their sockets, falls into those two layers. The way it interacts with the TCP/IP stack on your local system is where those two layers are present. It's just more of a, you can think of it as an experience layer for the network layer. And then you have the application layer. This is where our applications are actually defined. What applications I am referring to. This could be HTTP. This could be Exchange, which is a very legacy technology. I don't think anyone really uses it. We use Office 365 or Google Gmail or something like that. These are all applications, by the way. These applications are terminating HTTP. They're terminating requests because they either offer up that HTTP endpoint or an API. Now, if you look at that far right again, where we see all those technologies, this is where each one of those layers plays. The Kubernetes layer plays at basically the physical data link and almost network layer. But remember, once you stand up a Kubernetes cluster, what can it do? Almost nothing, especially if you do straight up kubeadm, or if you decide you're going to use some sort of automation. And the reason why that is because you also need a network. You have these little control plane entities that need to communicate with each other. So when those control plane entities come online, they need a network. What's that network? This is the container networking interface. You might be familiar with Cilium, Calico, Weave, Entrea. There's so many out there in the cloud native ecosystem, but the ones you'll probably most likely encounter are Calico and Cilium, or mostly Cilium. There's something interesting about Cilium and how it operates. But once you get past that network layer, right? Once you've gotten past signing IPs and applying policies at DNS, the application layer is where we start doing some intelligent routing, is where we can start implementing things like rate limiting, where we can start implementing some circuit breaking for our applications, because every service inside of your cluster is going to call on another service. We need to find a mechanism. We have a mechanism, which is a service mesh or a proxy, that allows us to control how traffic moves between these different services, how requests move. So anyways, this is a summation of what that, the OSI model is. And quite honestly, for operators, you're almost never going to engage with any of the layers below layer 7. Most of what you do is at the HTTP layer, and you're interacting with gRPC, for example, like the remote procedure calls or something to that effect, some other protocols that operate at that layer. And that's fine, because you will use things like policy, YAML, et cetera, to dictate how your network will look like, and effectively it'll just map to whatever subsystems that you have, Cilium, Istio, and then Kubernetes. So just to visualize aspects of a network, by the way, we are going to revisit networking namespaces. Oh gosh, I only have 45 minutes left. So we're gonna revisit this, but just to help you visualize, this local host here is a Linux node, standard Linux operating system, Ubuntu, whatever you want to call it. And it has a few things going on here. We've got the IP tables going there because it's actually going to do some filtration for us, some NAT, and some routing. We also have what we call a virtual bridge, which is denoted by @net0. That virtual bridge is present because it's emulating a physical switch. Are you all familiar with what a switch is? Okay, for those that are not familiar, at home you have a wireless network and you connect to it, and you have this box that you just has a password on it that you just use to connect to that network. That's a switch, but it's just a wireless switch that connects you to the outside world. Except in my case, I built a software-based switch, and this has been done many, many times before for the last 10, 15 years. So this is nothing special. But there's a reason why we follow this particular train. So attached to that virtual switch is what I call a network namespace. I have two network namespaces. One is called web app and the other one is called sleep. These network namespaces present a TCP/IP stack, basically a network card almost, to a process. Now what's interesting about this networking namespace is In Kubernetes, a pod is a networking namespace. This becomes highly relevant when we start digging into the way containers inside of a pod communicate with each other. So in this situation, I have two network namespaces. In Kubernetes, these would be two separate pods, each with their own IP. But if you notice the traffic path for a second here, this this web app endpoint, 192.168.52.2/24, we'll talk about the subnetting and IP addressing in a second, has to talk to 52.5. Who is 52.5? This AppNet 0. So it's using a default gateway, an entity that knows about everything else, because you don't know about foreign destinations, so you have to refer to someone who knows about it. So we'll use a default gateway to get to the outside world. That AppNet 0 is then going to take that request, that traffic, and basically there's some NAT going on, or network address translation going on, that hides the addressing effectively and then presents this to the outside world. So the outside world doesn't know about 192.168.52.2. All it knows about is maybe 192.168.52.5. And there's a reason for that too. There's various reasons for various things that we're seeing here. But this is the basis for how Kubernetes networking works. Okay, what are we gonna do in the workshop? I'm actually gonna skip a lot because of the time. I wanna focus in on core elements around routing, DNS, a little bit of HTTP. I'll take you through load balancing and firewalling, and then we'll talk about network namespaces again in a little bit more detail so you can visualize it on the command line, and then we'll end with actual Kubernetes networking to help you tie it all together. So I have my workshop ready to go. I think if you are following along, you should have yours also open and online. I just need to refresh this. And let me just do a ls. Okay, yeah, we're good. Okay. So if you're also following, you'll have a Linux terminal that's very similar to this, but you don't have to follow along. You can literally just watch me, and that's okay. And this is what I was referring to with respect to the OSI model versus the TCP/IP model. You can see that there is alignment between the multiple different layers across the two different models. But the reality is, when you want a true representation of where technology actually maps to, my previous diagram is probably one of the best to be able to visualize it. All right, so I'm gonna skip a bunch of this stuff because we're gonna revisit it. But what I wanna show you first is a payload. So this little data box here is what I call a payload. It contains a request, an HTTP request. But who is carrying that request? So in order to carry this request, I have to wrap this request in what we call an IP address. And there's a host name behind it, but an IP address. Because I have to route to it. I have to find it. I have to be able to interface with it through IP networking. So I wrap this in what we call a packet. Or not a packet, sorry. This is what we call a transport layer segment. And that transport layer segment basically dictates what application and port protocol is being used. So in our case, this payload and the request is HTTP. Therefore, HTTP is a TCP-based protocol, and it'll use port 80. So there are two types of transport protocols. One is TCP and one is UDP. TCP is Transmission Control Protocol, while UDP stands for User Datagram Protocol. What is the difference? With TCP, every time I decide to communicate with someone, I need to wait for an acknowledgement to come back. If I don't get that acknowledgement, I have to assume that that other endpoint is not alive or not available. This is great because I can gain reliability in the communication. I can verify that I'm communicating with some other endpoint. But this also creates slowness. This adds latency because you have to verify every single time you send a packet over. On the flip side, UDP is the opposite. It doesn't have reliability. It just fires away packets. And why that's important is because there are certain applications that cannot tolerate that acknowledgement. So voice is a perfect example. Voice over IP is a perfect example of using UDP. Now, what happens when you have a bunch of dropped packets in UDP? Well, it's not UDP's responsibility to make sure that that connection is reliable. You can use upper layer protocols. So there's RTP and some other voice-related protocols that make sure that there's reliability in the underlying protocol. So, and that's perfectly fine. It's an acceptable model altogether. But the reason we have these different kinds is just for the different types of applications that exist. We can't always expect an acknowledgement for certain types, while others we have to because there might be some security requirements or the way that transaction between those two endpoints communicate or happens or occurs. So we've wrapped it in a transport layer segment, and then once we've identified that protocol, we have to map it to a packet. So this is the carrier. This is the actual carrier with a logical address, an IP address. I have this request that's mapped to an IP address because you have this source that's sending this request somewhere, and you have a destination that's going to receive it. So in our case, we have a source IP of 192.168.1.33, which is sending this request to 54.208.105.16 using the TCP protocol. Now, once it does this, it can know that it can communicate with that TCP-based application and that endpoint. But wait, it doesn't stop there because the actual address, that logical address that I showed you, doesn't tell me the actual hardware that I'm going to be ending up at or terminating at. And this is where we have to wrap that packet in what we call a frame. So that frame contains the MAC address of all the different hops, source and destination hops, that has to carry that packet all the way throughout. It's a lot to actually explain how this swap occurs, but when that packet has to move along multiple different networks, the source and destination MAC addresses will always change per hop. There's a reason behind this is the way packets are learned, or sorry, frames and devices are learned on a network. And this is all about MAC learning and MAC address tables and the storage of this information around entities. And this is why this data has to change and transpose every single time. So we have this payload, we have to wrap it in a packet, assign that transport layer protocol, and make sure we assign it to a hardware endpoint and source so we know how that packet is moving all the way throughout. But that's module one. That's basically how TCP/IP works. We're done. Take care, everyone. I'm kidding. Okay. The next module is where we're going to get a little bit deeper because we have to understand how traffic moves around the network. So if you recall earlier, I made a mention of the fact that when my laptop connects to a web browser and connects to some website, it's some remote entity that I have to connect to. So all I'm giving it is, let's say, google.com. But where's google.com? So in order to get to google.com, we have to know the IP address of google.com. So there's a DNS translation that goes on. I cover it in the next module, so we'll come back to that. But now we have to understand how packets move around the network. So we'll focus on the network layer, and I've already talked about MAC addresses, but let's talk a little bit about subnetting. So your home networks probably have this addressing 192.168 something.something. And that's standard for a lot of home devices, which is okay. But when you have that address, it's known as a private subnet. Private meaning you can't route that private subnet on the public internet, because there are public addresses that you would use to route on the internet. There's this separation because what we wanted to do is have multiple devices behave and be available on a network, be able to communicate amongst each other and then outside. The reality is there are not enough public IP addresses in that public space to hand out to the billions of devices that exist in our network today. Like multiple billions. I'm not talking about a single billion, multiple billions. For every person out there, you can assume five IP addresses. So how do you route all of these entities across the network? Well, you need public addresses, and you need this concept called NAT. So network address translation will take your private IP address and translate to a public IP address. There's a lot more to it, but I won't get into it now. We'll talk a little bit more about ports later on. So I have these private subnets that I'll route outbound using NAT to get to the outside world, but I have to assign addresses to my endpoints. How do I do that? There's something called DHCP. You'll have a DHCP server that exists on your network, and whenever your device comes online on the network, it'll go ask the DHCP server for an IP address so it can communicate on the network. What ends up happening is your endpoint, your computer, will be assigned an IP, subnet mask, a default gateway, and a couple of DNS servers. The DNS servers are important, and we'll talk about that in the next module. But for now, let's visualize routing for a second. So in this little environment, I have two networks, the 192.168.52.0 and the 10.13.37.0. The /24 just dictates how big that network is. We can spend like 3 hours on subnetting. I don't have 3 hours, unfortunately, but if you want to find me later on, I'll take you through some subnetting basics. Now, across these two networks, they need to be able to communicate across to each other, but they don't know about each other. So they have this intermediary device called a router or a gateway. That gateway has feet in both of those networks, so it knows about both of those networks. Having that information, it's able to carry any sort of request from, let's say, app 1 over to app 3. How this works is app 1 has a default gateway of 192.168.52.1. It might have an address of like 52.3 or something like that. But it's going to make a request to app 3. It doesn't know how to get to app 3, so it's going to ask its default gateway, hey, how do I get to 10.13.37.3? Well, the router knows about it. The router's like, no problem, I'll take you over there. So the router carries that request over, and at the same time, there has to be return traffic, especially if it's TCP based. So if there's return traffic, the router is now responsible for making sure that there's a return path, which it knows about. So there's bidirectional communication in this setup. Networks don't look this simple. There's so much more to networks. There's so many networks out there. And there are so many of these intermediary routers that exist. Now, when we have intermediary routers that exist between these routers, we can't manually define how to get to all of these networks across each of these router hops. Each router is a hop, by the way, because you have to traverse these hops to get to other networks. So in order to learn about other networks, remote networks, we use routing protocols. So there are a few out there. Who can name a routing protocol for me? Go ahead. BGP? Yeah, BGP is a, yeah, go ahead. Yeah, RIP is, yeah, RIP is RIP. So yes, there's BGP, there's EIGRP, which is proprietary, there's RIP, there's OSPF, there's ISIS as well. There's also some legacy protocols. But all of these protocols effectively communicate routers with each other. They form neighborships, and these routers talk to say, I know about these networks, so I'm going to tell you about them. You just maintain that database. And if you have like other neighbors that aren't directly connected to me, well, you'd share that information with them. So because of this, now you have this global routing environment that everyone knows about each other. But it doesn't stop there, because there are inefficiencies with the path that you might take, and that could go on forever. Anyways, every router and every endpoint, your MacBook has something called a route table. That route table basically says, this is how I get to that network using this exit interface or this IP address. And we'll see a route table very shortly. Talked about default gateway. Loopback route is basically a route to itself, to its own endpoint. So if you have something routing to itself, it's just saying use localhost to get outbound or get anywhere you want to, or basically answer the request. That's all it is. And it's used in a lot of different situations. Talked about routing protocols. Let's configure routing. Okay. So if you're following along, we need to install NetTools, because we're installing things like routes and the IPNet and Nest capability, because I have to create 2 network namespaces in this module to be able to demonstrate the routing aspect of it. I also need to turn on IP routing or IP forwarding in the Linux kernel. And this is not to get outside to the outside world. This is actually to allow these network namespaces that I'm going to construct to talk to each other or to route to each other. So the moment I run that systemctl-w.net.ipv4 IP forward equals 1, I ran two commands. One is netstat-nr, and that's a legacy command. You'll probably never use it. Another one I ran was route. They provide the same output, and they're basically outputting the routing table, which I just described. So this is how you get to various destinations or networks. There is a step here that I was going to deploy a static route. I'm not going to do that because I'm just going to save some time, but I'll explain what that's actually doing. When you add a static route, you're manually defining how to get to a destination. Static routes are great temporary Band-Aid fixes. But the more static routes you have, you're just putting Band-Aid upon Band-Aid upon Band-Aid, and then you have this mess of routes that you don't know which one's actually the most correct route, most believable. This is why routing protocols exist. The other thing too is it's difficult to maintain across a fleet of routers. So you want to either automate it or use a routing protocol. Now, in our case, we're going to stand up two networking namespaces, and I'm going to clear my screen so I can explain exactly what's going on. So I am, in the first line, defining two network namespaces. Each of these network namespaces is going to attach directly to each other, but they're going to have their own, yeah. Oh, you want to make it bigger? Okay, yes, let me do that. Ooh, if I make it too big, I might not be able to fit it all on the same screen. Dang, okay. Let's clear that. Let's try this again. There we go. Is that better? Awesome. So I have a few commands here that basically assign interfaces to these respective namespaces, and then on top of that, I assign IP addresses. Don't get hung up on the actual address, especially if you're a networking person and you know like not to assign network addresses. I've assigned network addresses, but it's just for demonstration purposes. You wouldn't assign these directly. You would actually assign an address inside of the subnet, and this goes back to subnet calculation and capacity planning. Anyways. So I assign addresses to each one of these network namespaces. I'm going to bring these interfaces up, and I'm going to turn on their loopbacks as well. So the moment I deploy this, why am I typing kubectl? I'm on a Linux terminal. I will get to kubectl later on. So the moment I run this, I can actually go ping, but I can't. I can't reach that remote network. And what I've actually pinged from is I've actually exec'd into exec, kubectl exec, docker exec, ipnetns exec. It's all the same command, by the way. It's just, I think Kubernetes is a bunch of labels in disguise, but that's a different story. So when you do a ping -6 10.13.37.128, that's the remote network of the web app, the endpoint. I can't get to it because I don't have a route to it. If I try from the web app to the sleep, same situation. So in order to fix that, we actually have some routes that we'll add. And I've gone ahead and added the route. So I basically just exec'd into the namespace, and then I've just said route add the destination network and the interface I'm going to exit out of. The reason I specify an interface that I have to exit out of is because that interface knows about a network it can, or another entity like a default gateway that can go out to the outside world. So we can look at the routes, and it's going to look a little interesting because it doesn't actually, oh, it does. Okay, so it does spit out that it's connected to a local network and that it has access to the remote network. So it knows about it because we've manually plumbed those routes. So if I go ahead and do a ping, I mean, yeah, it says it works, but it should work. And I expect it to because there are routes to each other. There's a bidirectional pathway. So if you were to do this in the physical world, right, what you would do, not that you would ever buy a router or something like an actual Cisco or something like that, but you could go on eBay or something and get one. You would connect one computer to one of those switch ports on the back of that router. You connect another computer to the other switch port on that router. They'd be on their own networks, and you would do the exact same static route command once you logged into that router. Assuming that you've assigned addresses to your endpoints, you're basically mimicking this. You can do the same thing with virtual machines if you want to. I'm not going to describe that process. You'd have to build a virtual network, and you could do that with Linux and Proxmox or KVM, whatever the heck you want to use, but you can do it in any way, shape, or form. Now, I'm illustrating this because when we go back to network namespaces, what's interesting and what happens is, damn it, I have 25 minutes left. What happens is, this is a repeatable process that you can't be doing manually, so you have to automate it. All right, let's move on to DNS. Any questions while I'm loading the next module? All right. So it's always going to be DNS. And if you understand that example I just described earlier on around how my web browser connects to, let's say, google.com, google.com is a host name I'm familiar with. I don't know its IP address. So on my local system, I'm actually going to do a lookup on my local host. If I don't have a local host entry for where google.com is, and I don't know the IP address of it, I need an upstream DNS server to resolve that for me. Now, let's be real. Your most direct DNS server is not going to have all the answers to that translation. So in order to get that answer, sometimes it has to go to upstream DNS servers and top-level domain servers to find out where that actual endpoint is or what that entry is, because we have to get that A record. An A record basically takes a host name and translates this to an IP address. Once we have that IP address, we now know we can route to it because we'll use our default gateway. Our default gateway would assume that it knows how to get to that destination, and now we can get there. So that's DNS in a nutshell. There are a few types of records you'll encounter. There are A records, which, like I just mentioned, host name to IP address. There's a quad A record, which maps a host name to an IPv6 address. I didn't talk much about IPv6, but let's be real. Are we ever going to use it in the next 5 years? Probably not. Not that much anyways. And then there are other records like a PTR record, which does the reverse of what I just described. There's a canonical name or a C name, which takes one record and then maps it to another net record or another name. So you can have multiple names for the same destination. There's this concept of fully qualified domain names. And this is important, especially in the world of Kubernetes, because in Kubernetes, DNS resolution happens through the mapping of your services with your actual deployment, with the namespace it's assigned to, and just a few other bits and pieces. But quite honestly, as long as you follow this methodology for understanding your hosts in DNS inside of Kubernetes, you'll understand how to, let's say, call on resources inside of your environment. Now, there are a few tools that can be very useful, especially if you're troubleshooting. Let's say you're trying to resolve some addresses. You can use dig. I'm not going to use NSLookup. We're going to use dig. And when you do dig, right, dig google.com, dig actually uses the local DNS server to resolve google.com. If it can't get the answer, it'll go upstream to find that. Now, I can also specify, what's a DNS server, 8.8.8, and then type in ibm.com. And what this does for me is that it's going to use another DNS server to resolve my answer versus my local one. So it knows how to resolve that pretty easily. And this is pretty powerful because from a DNS troubleshooting standpoint, you can evaluate if your local DNS server might be offline, might have issues, a lot of other things you can do. That's the extent of DNS. The reason why I bring it up is because when we get into how services work inside of Kubernetes, this becomes highly critical in the way we communicate with them. So, any questions about DNS? It's always going to be DNS. All right, let's move on to HTTP and curl. Because when you are working with applications, your applications are making API calls across what protocol? TCP, but HTTP at the application layer. So with HTTP, we have headers, we have information we can inject into those headers, we have different kinds of methods that we can do against different services, and then we also have messages that we get, right? So let's talk about the request methods quickly. The request methods you're probably familiar with if you're a developer, the get, post, put, delete, patch, etc. These are just basically actions or verbs that allow you to take action across another API. I want to get information from that web service, so provide me the output. I want to delete information. I want to put information or patch it, something along those lines. But the reason this is important is this is how all services communicate. For soliciting information, for it to process that information and do something with that data and output it elsewhere. But there's also another reason, for policy. If we didn't have any policy in place, all of these services might be able to make all kinds of calls to other services, which could be an inherent security risk. So you would use authorization policies to only limit who needs to do what to what other services. It's more like an RBAC/zero trust model. Now, there's also the status codes. So there's several different types, 5 actually. There's the informational, which is the 1XX. There's the 200 success codes. There's the 300 success or redirection messages. There's the 400 client-side errors. And then there's the 500 server-side errors. So depending on varying conditions, you might get any one of these messages. If all is clean and all is well, you should expect an HTTP 200. If you have a proxy in between that filters requests because you're missing a JOT token, that might be a 403 forbidden. You might be rate limited with an HTTP 529. Is it a 529? Yeah, it is. 429, you're right, sorry. Too many requests. So there might be an instance where to prevent a service failure, your service has to be resilient. And so if you receive a number of requests in a certain period of time, okay, you're at your limit, you're at your capacity, do not accept any more requests. Return this message to the client saying, well, you're SOL, because you have to wait for this timer to expire before I can process your requests. Now, on the other hand, there might be server-side errors where the actual service might be unavailable, or there might be some circuit breaking going on, things that you can influence. You can pass along these kinds of status codes as well. So there's a lot of interesting data that you can pull from these status codes if you're trying to troubleshoot service resiliency, or why there might be latent operations, or various other things as well. Now, think about metrics and monitoring systems. They use HTTP metrics to determine if a system is online and healthy, right? So this is valuable to know if you're in networking. This is extremely valuable because I think in the networking world we've overlooked this for a long time and only now see the importance of it. So I'm not going to curl right now because I know you all know how to curl, but curl is a utility to allow us to make calls to endpoints using HTTP. We can manipulate that curl command with different parameters to pass in header information, authentication information, other metadata, so that we can indicate ourselves uniquely to that endpoint that's going to process our request. That's it about HTTP. Let's dig into load balancers, firewalls, and proxies. Yes?
In case of you're using HTTP, you use DRCP, you can use gcurl with the same
zcurl.
For
yeah. Gcurl, yeah. Thanks for mentioning that. I appreciate that. Okay. So this module, I'm getting nervous with the time. I feel like I'm going to run out. Okay, so firewalls, proxies, and load balancers. I'm not going to dig into the actual details of on the command line because of time. It's going to take some time. But how many of you are familiar with what a firewall does? Put up your hand. I just want to gauge the audience. Okay, so a firewall is a filtration device. It normally sits at an edge of a network or an edge of maybe even your laptop. You might have a host-based firewall. But this firewall is responsible for intercepting traffic and evaluating a rule set against it. So if there's a policy that matches that inbound request or inbound incoming communication or connection, it's going to evaluate it. If it aligns to any policy that denies it, the firewall will either reject the connection, drop the request or packet, or return a message to the sender saying, hey, your request has been denied, or your request has been rejected. So this is interesting because this is a security tool that we would use at the edge of our network. But the reality is, let's say you pull down containers into your environment from unknown destinations. You're like, yeah, I'm going to pull this, I don't know. Give me an example container that you would put. Nginx. I'm going to pull down Nginx. But when you do let's say kubectl run Nginx or something like that, how do we know that it's going to resolve to the right legitimate Nginx golden image without vulnerabilities? We don't, right? We don't. So let's say it does pull down this malicious container that pretends to be Nginx. Now it's in your network because you don't have policy in place. It has free roam. It can talk to other pods. It can manipulate other pods. It could even maybe potentially run as root, right? On the Linux operating system too, on the local node. We don't want that because now it could basically infiltrate your entire network at that point. So this is where firewalls come in. We obviously don't want to stop at just the edge. We deploy firewalls within the network as well across all of our workloads. This is what we call east-west firewalling. So in Linux, there are a few types of firewalls. There's IP tables, which is heavily used in Kubernetes. If you're using, let's say, Cilium, the Cilium CNI in Kubernetes, you have the option to not use IP tables. You can use eBPF to process a lot of that. Sidebar, what is eBPF? Yeah, you want to go for it? Go for it.
Like inject instruction directly to the kernel.
Yeah, so basically creating a sandbox program that runs alongside the kernel, accesses the kernel, can hook itself into the kernel to look for events. The reason we do this is because this can operate faster inside of the kernel space versus in the user space. Especially when we're talking about software decisions or like routing decisions happening in software. If this can happen at the kernel, this is why eBPF is going to, help optimize that. Anyways, IP tables does this now as a default. You can use eBPF if you decide to use Cilium or even Calico for that matter. But there's a whole bunch of chains that your packet or your traffic has to flow through. I'm not going to describe all of them. I recommend taking the workshop. But it's different processing of that traffic. So we'll evaluate policy on whether or not the traffic is allowed, all the way to whether or not we're going to forward it to the destination, to are we going to NAT this, et cetera. So that's firewalling in a nutshell. Let's talk about load balancing. So why do we use load balancers? Yeah, redundancy, high availability. We use load balancers to even proxy and terminate communications and connections on our behalf of our apps. So with the context of load balancers, in let's say a cloud environment, when you have multiple different apps or you have multiple copies of an app, you'd like to stick a load balancer in front of it. It might be a network style load balancer, it might be an application level load balancer, or some very classic TCP or IP-based load balancer. It could be just a very basic generic IP-based one, which quite honestly, all it's really meant to do is distribute the load or fail over, right? That's all it's really going to do. But that concept has been brought directly into the world of Kubernetes because we know we can take pods, scale them, but as we receive incoming requests, how do we route them to all of them and not just one? This is where the load balancer comes in. So the load balancer is intelligent enough to decide, hey, I can distribute the traffic in a round-robin fashion or based off of conditions where, let's just say one of those 3 pods tends to just disappear and then come online for some reason because of the loss of network connectivity. It's marked as unreliable. So I will send less requests to it and more to the other 2 that are more reliable. So that's effectively how a load balancer functions. Now, when we're talking about Kubernetes, there's load balancing for services inside of your network, inside of your cluster, so that we have service availability all the time. And we use this concept of Kubernetes services, cluster IP, node port, and load balancer service. Now, when you actually use the service of type load balancer, that's a call for an external load balancer from your cloud provider. Technically speaking, I don't know why they call it load balancer service because the reality is all we're creating is an external connection for folks to find their way into our cluster, right? And we use a load balancer to do that. But there are other tools out there, like if you look at ngrok or inlets, or if you look at, what's that other one? Anyways, those are 2 that come to mind right now. They actually provide you the load balancer service. Oh yeah, it's because my screen just went black, but that's okay. They give you that load balancer service, but all it's really doing is giving you an outside IP so that you can expose your application and whatnot. But it doesn't stop there when it comes to load balancing because load balancing goes beyond that. It really comes to this idea of, okay, if I even have multiple copies of something, I also have to think about the geolocality of it. So if I spread my application globally, right, I can't use one load balancer on one location to try and load balance across the globe. It doesn't work. But I could use a global load balancer that maps to sub-load balancers, and that can help me route requests intelligently based off of where requests are originating from. So if I'm in Canada, why would I hop all the way to London to access an app? I would do it locally. And that's tied to this concept of CDN and using Anycast, which is outside of the scope of this workshop, but find me later if you want to know more about that. So load balancing is we're going to talk a little bit more about it in the context of Kubernetes very shortly. But inside of Kubernetes, you'll have 2 kinds, basically to allow your pods to be load balanced and to expose your pods to the outside world. Oh, and by the way, providing high availability for your cluster, because if that goes down, you're SOL too. Okay, let's go to network namespaces now. And while that next module is loading, I'll talk about proxies. Proxies are like routers, which effectively do the function of a load balancer as well as a firewall. Why proxies show up, especially in Kubernetes, is because you normally would deploy a proxy, an ingress proxy, to decide how you want to route to different services in your network, to filter, to do web application filtering, like using a WAF, to do rate limiting on the ingress, to do some sort of TLS termination. That's what a proxy is doing. It's proxying connections on behalf of your app. The reason why this shows up in this workshop is because proxies are actually pretty damn important with respect to service meshes. So in the world of service mesh, there's this model called sidecars. Sidecars are effectively mini proxies deployed inside your main application container inside of a pod. But it's interesting because that container, that proxy container, shares the same networking namespace as that main container, which means they both have the same IP. So how do you differentiate the two? Port numbers. So if you have different ports, they have to be different ports, then they are unique entities inside of that pod. But inside of the world of Kubernetes, Kubernetes treats that pod as a single pod resource and will lifecycle it. So your containers are lifecycled together inside of that pod, or reconciled, or whatever it is. Now, in the case of service mesh, that proxy is deployed to intercept connections, to process policy, to provide MTLS, authenticate requests, authorize requests, etc. So it's like your mini firewall doing everything in one. Except in the world of today, there's both methods. You can do proxyless or proxy-based. So, all right, let's talk about network namespaces again. So in the case of networking namespaces, I'll walk you through building it because I don't really want to build it all out. And the reason why that is because time. I don't have much time left. I have like 8 minutes left now. So in order to build a networking namespace, I have to define a networking namespace first. We saw it earlier on. Then we assign it an IP address. And then we can attach it to a bridge, and then that bridge has an IP address too. That bridge has a gateway to the local host. It'll use the local host through NAT to get out to the outside world. Now, when I build this network namespace, and if I want them to be on the same network, I actually have to establish virtual Ethernet pairs or wires, virtual wires, that connect one end to the network namespace and the other end to a bridge. If I have 1,000 containers, do I want to be sitting there doing that all the time? So yes, we don't want to do that. We can automate that. But there's the other side to it too. If I have to offboard these containers, take them offline, kill them, destroy them, I have to reverse the process again. So I have to delete the network namespace, but before I can delete it, I have to unattach it from the bridge that I've attached it to. Then I have to remove the virtual wire. I have to delete the interface that's assigned to the namespace and remove the IP addressing information and then delete the namespace. So that's not something we want to do in the world of Kubernetes, which is why CNIs exist. So CNIs, Docker actually did this first. Docker actually automated that whole networking namespace configuration. CNIs conform to a spec. Container networking interfaces conform to the Kubernetes networking model spec, and that outlines how a network namespace should be formed and what a CNI should be providing. Basically, IPAM or IP address management, discovery of pods. When a new pod comes online, assign it an IP, and then when it goes offline, remove the IP and make sure that the IP does not get released back into the pool for identity purposes. We don't want to allow someone else to assume the identity of that previous pod and do some malicious things. So that's network namespaces in a nutshell. I highly recommend you go through this module if you want to at your own time, so you can understand the pain of having to manage and lifecycle a network namespace, or pod networking, I should say. Okay, the very final module is, I've got 6 minutes and I think I can wrap it up in 6. So the very final module actually brings us to Kubernetes networking at this point. So what we want to do is we want to deploy a couple of pods and see how they communicate with each other. Pods get IP addresses, right? I don't need to describe what Kubernetes is, do I? Good, excellent. Okay, so in our environment, we already have a few we have a cluster and a few nodes. So kubectl get nodes, and you can see I've got a control plane and 2 workers. So we can inspect the subnet that we're using for assigning IP addresses to these pods, any pod for that matter. And the network that we're actually using is 10.42.0.0/16. That /16 just means that I have 65,000 available addresses to assign. In the real world, you don't want to do this. There's reasons why. Find me later and we can talk about it. But that's what this configuration is telling us is I'm going to take from this pool and assign addresses to any pods that come online. Now, I'm not going to grep the nodes or do anything here, but what I want to do is I'm actually going to demonstrate to you a deployment where we have two pods that need to communicate with each other. So if I do a kubectl, let me minimize this, kubectl get pods o wide. And if I spelled wide properly, that would be great. So there's an example pod, right? It's got 2 containers out of a total of 2 containers. So with a single IP, how do I communicate from one container to the other? So let's look at the configuration of the 2 containers. Exactly. So if you see here, container port is 8080 here, and then 8081 over here. So it's not like I'm going to run a ping between these 2 containers. I would use curl. So I could exec into the pod in one of the containers and then curl to the IP and then output the contents of that application, assuming I have the right port number. So I think we're going to do that right down here. So let me just clear my screen. So I'm execing into the first pod, or the only pod, into container 1, and I'm just going to output the IP addresses of both containers just to see what shows up. And you see that they both have the same IP. That's expected. Let's just do a quick, this is a call. All right. This one, I'm actually running a curl. So if you see this curl command, darn it. That's not what I was supposed to do. Yeah, don't click on that URL. That curl command basically is just saying, if I exec into this pod into one container and I run this curl against localhost, if I run it against myself, well, it'll resolve. If I run it against the other container in that pod, it should also work. Because who is localhost? My local namespace. And we see that works. So inside of a cluster, inside of a pod, this should be a no-brainer. If I have 2 pods on the same host communicating to each other, that should also be a no-brainer. That should work properly as well, much like how this would work. If I have a pod on one node in the cluster and another pod on another node in the cluster, how does that communication work? What's that? Not necessarily. So if we have to think about the lower layers for a second, because when we're thinking about how these nodes are tied together, what are they providing for these pods? They have to provide these pods in network. It has to be a common network. So in the world of software-defined anything, we have this concept of software-defined networking.
It's a bridge.
It's a bridge, but we also have to create these VXLAN tunnels, or tunneling between nodes. And by creating these tunnels between these 2 nodes, or multiple nodes, it treats them as one large broadcast domain, quote unquote. And the reason for that is to allow these pods to operate in the same IP subnet, despite the fact that they might be on separate nodes. So what ends up happening is pod 1 on host 1 will go through host 1's local TCP IP stack, will get tunneled in something called VXLAN, because we're using flannel today. And that tunnel terminates on the second node. That tunnel, because it terminates on the second node, unencapsulates or decapsulates the payload and then forwards it onto the destination pod. That's how it works. Now, in other CNIs like Cilium, that option is there as a default. You can actually turn off that option and do native routing, which means those IP subnets that the pod siders have, like whenever you assign an IP address to a pod, it's coming from that pod sider, that can be advertised into your public network. So now not your public network, but the rest of your network, your upstream, your, what's the other word? Your northbound network is the right word. When you do that, why that happens is because you're effectively telling the rest of your network, hey, this is how you reach these pods, right? This is how you get to them. This is more of a routing situation because now you're using BGP as a protocol to be able to interface. There are no other protocols that support this today in Kubernetes. You could probably automate it through a bunch of API calls. But the real purpose of that is maybe you don't want to use VXLAN. Maybe you have a very complex global network, global private network, and you have these specific legacy workloads that they're containerized, but they don't really operate at the HTTP level. They're stateful. There's varying conditions, right? They're unchangeable IPs, so I always need to get to them. And this is why we use things like VXLAN to extend our layer 2 broadcast domain. There are other ways to do it. There are better ways to do it. But this is a method that Cilium takes, for example. So to wrap up, there are a couple of other artifacts that I'll just briefly talk about. I talked about service networking, but there's also this concept of ingress networking, because here's the reality. If you have a bunch of services that exist in your cluster, are you going to provision a single load balancer for every single one of them? Absolutely not. So you'll use an ingress resource, and then you can determine based off of host name how you map these host names and their destinations to actual services inside of Kubernetes. Now, the traditional approach was to use the ingress resource in Kubernetes. Today, it's the gateway API spec, which is a very similar approach. It's just more of a standardization so that API gateways, not gateway API, they're two different things, by the way. API gateways and service meshes can conform to this gateway API spec for ingress networking. That being said, Istio as a service mesh has both its own proprietary option and the gateway API spec option. So you can basically take one load balancer and overload it with multiple services so that you're not over provisioning your load balancers. But this is where it ends, because if we decided to go any further, then I'd be talking endlessly about service mesh and how all of the stuff that I just described becomes pretty much hidden once you start deploying Kubernetes, or pretty much a lot of cloud environments. I go deploy a GKE cluster. Are you sitting there deploying the networking namespaces for the control plane pods that come online in that cluster in addition to the subnetworks that operate? No, you're not. It's all automation at this point.